Moore's law is already showing signs of exhaustion for some time. The silicon, the main component used in the construction of the processors we use daily, is already reaching the physical limits inherent in the structure of that material, with the miniaturization of elements within the chip begins to lose its electrical conductivity characteristics so necessary for the functioning our CPUs. The third generation of Intel Core processors, codenamed Ivy Bridge, already has an impressively small lithography, 22 nanometers. Just to give you an idea, this means that each transistor was measuring 1 to 4 the size of the flu virus, which is 80 nanometers. Because of the reduced super size, the company had to build its chips with the new 3D transistors technology to standardize the behavior of electrons and increase the energy efficiency of the processors, since the scale of magnitude would not be possible to build such small objects with planar transistor technology that has been used for years. Many solutions have been proposed to replace silicon as the main component going graphene quantum computing, and the second has started to show very promising results. Current processors may be regarded as tiny lamps where the erased is 0 and lit is 1. These little lights are transistors, and the speed and amount that they change their state is what allows our computer to perform the calculations with which we are accustomed. In computing, quantum bits or qubits have not only 2 states, but a multitude of them between 0 and 1. Just a slight variation to achieve a state change, so most operations can be performed at once, so that computers equipped with future quantum processors have the potential to be millions of times stronger than the most modern supercomputers we see today. Although the idea of using quantum physics in the construction of electronic devices may seem science fiction story, this concept is a very similar shift from vacuum tubes to transistors, a fact that at the time was seen as strange by most but turned out to be a pattern. They have been developed computers capable of running on only 16 qubits, which may seem little, but these machines have superior performance to processors that have currently available. Encryption is another area that has a lot to gain from quantum computing. Virtually unbreakable algorithms can be developed with the help of quantum physics concepts, and in the future, we may have machines with more processing power than we can handle. What do you think of quantum computing? Do you believe it will be the future of computing? Beginning. In the 20th century, humanity has followed a moral, technological development which is reflected in several areas of knowledge and activity sectors. A fact that many people are unaware of is that the great technological leap made by man in the last century was based on the 2 great intellectual triumphs established in the same period. The 2 first scientific gifts that preceded the technological breakthroughs that have changed the man's lifestyle are quantum mechanics and computer science. If today we have ever faster and more powerful computers, electronic equipment that allows adequate medical diagnostics, among many other electronic devices that have improved our quality of life, we thank all the scientists who in some way contributed to the development of these 2 areas of knowledge. Amazingly, the Great Revolution mentioned in the previous paragraph started in a crisis that physics went through in the late 19th century because some natural phenomena were not explained by physical theories then existing in this period. In this scope, there is a precise date for the birth of quantum physics. It is the day, December 14th, 1900, when the scientist Max Planck explains the radiation emission of the black body. The explanation was prepared by Planck based on the assumption that the walls of the cavity when radiation emitted packages, which would be integer multiples of a certain minimum amount, that is, the radiation should be quantized. A few years later, in 1905, the German physicist Albert Einstein, renowned, elucidates the photoelectric effect, which was another phenomenon not explained by the wave theory of light. The photoelectric effect is the emission of electrons by a metal surface bombarded by a beam of light. Although many of us do not know, this effect is very familiar because it is present in our daily lives, such as doors that open and close automatically have the operation based on this phenomenon. Einstein explained the photoelectric effect admitting the hypothesis that light consists of the concentrated energy package, which now call photons, and thus the phenomenon in question is easily explained when we consider the collision between the photons of the incident radiation and the electrons of the metals. It is important to note that Einstein and Planck's quantization work suggested but did not explain why. A similar problem arose when the Danish physicist Niels Bohr in 1913 introduced its atomic model, which assumed that the electron could move only in certain orbits which do not emit electromagnetic radiation. The radiation was emitted only when the electron jumped from one orbit to another. With this model, Bohr solved the atomic stability and explained the discrete radiation spectrum for a hydrogen atom, but it was not clear why the electron cannot occupy intermediate positions in space. Thus, through these examples, we see that quantum theory developed by the first quarter of the 20th century had fragile theoretical and conceptual bases because the principles were sparse and the statements were created with a specific purpose to meet a particular need. In this scope, the physical resented authentic postulates and general principles of which could formulate a consistent, efficient and comprehensive theory. This desire of the physical became a reality with the advent of quantum mechanics. Quantum mechanics is considered the most successful scientific theory of the history of science. It is due to infallibility. So far, their predictions are verified by experiments. Quantum mechanics is the physics theory used to treat microscopic particles in the order of atomic or molecular size, because if we use Newton's laws to analyze the behavior of particles in this size range, we will reach the inconsistent results with the experiments. Thus, quantum mechanics is the basis of atomic physics, nuclear physics, solid-state physics and modern chemistry, in the sense that it is not surprising that a large number of appliances with added technological value have their principles grounded operation in quantum mechanics. To get an idea from the post-war, about a third of the US gross domestic product comes from the application of quantum mechanics. Thus, when we look, for example, modern mobile phones and televisions and various other electronic equipment, we must remember that come from the vast applicability of quantum theory. And yet, some projections indicate that from the second decade of this century, most of the jobs in manufacturing in the world will be connected to nanotechnology, and to work on this scale is essential to a sound knowledge of quantum mechanics. We mentioned the two great intellectual triumphs of humanity in the 20th century. However, until now we treat only one of them. So let quantum mechanics a little aside to enforce us computer science. In a way, we can say that computer science was born with a remarkable article of the English mathematician Alan Turing in 1936. In that work, Turing developed the abstract notion of what we know as the programmable computer, which became known as Turing machine. This essential Turing proposed apparatus operates with logical sequences of information units called bits, binary digit, which can acquire the values 0 or 1. Turing's idea was so important to the development of humanity that the computers we use today, from simple notebook we use at home to the most powerful computer of a large research center, surely these are a physical realization of the machine Turing. Thus, all information provided to a computer is read, processed and returned in the form of bit sequences. A fact that reveals the power of the Turing machine is a result of the so-called Church-Turing thesis, which states that the Turing machine, although simple, is capable of solving any computational problem solvable by any other type of computer. This argument implies that if there is a problem that is insoluble to the Turing machine, such a problem cannot be resolved by any other type of computer. The Church-Turing thesis says that we do not consider different devices of Turing machine to find out if a problem is computable or not, but the theory does not say anything about the time needed to solve a problem that can be computable. It enabled computers to evolve in speed, but without losing the fundamental principle of operation based on bits. In this sense, as we shall see in this work, there will come a moment in the evolution of computers that the merger of the two intellectual assets mentioned in this introduction is inevitable. This great event will open the door to what we call quantum computing that could revolutionize the current way humanity treats the information. Thus, the aim of this is to present quantum computing, giving their use in schools of primary education as well as in informing the public in general. The Moore Law. There is evidence that the first programmable computer emerged in 1941 during World War II, and its invention is attributed to the German engineer Konrad Zuse. The computer developed by Zuse was named Z3, and was entirely mechanical so that the information was processed by the motion of gears. In the same period, scientists from Britain and the United States also worked on similar technology projects and thus developed two critical computers for the evolution of computing, respectively called Colossus and ENIAC. The significant development of computers about the Z3 was the use of electronics, which enabled a real increase in processing speed because currents and electrical charges can be handled faster than the Z3 gear. However, it was the discovery of transistors enabled the development of rustic computers, as described above, to what we have today. The fact is that the notebook I used to write this text is about 10 million times faster than ENIAC and much lighter, given that the ENIAC weighed 27 tons. Even with relevant differences in processing speed and weight, my notebook and ENIAC use electric charges and currents to store and process information. If we analyze this evolution of computers using a more efficient parameter for our purpose, we had in 1950 were needed in 1019 atoms, that's right, 10 billion, to represent a single bit of information. Some projections indicate that only one atom will constitute a bit in a few years. These forecasts are based on what we call Moore's Law. Gordon Moore, the founder of US company Intel Microprocessors, noted in the 1960s the number of atoms needed to represent a bit is reduced by half about every 1 year and a half. It is equivalent to saying that the number of transistors on an integrated circuit doubles every 18 months. As an example, we can mention the Intel 8086 processor. In 1978 had 29,000 transistors, while the Pentium 4, launched in 2000, had 42 million. The laptop processor that I use in my day-to-day has nearly 1 billion transistors. From the physical point of view, Moore's law imposes a natural limit to computers because it was reached the limit of 1 bit per atom from the moment there would be more to increase the bit density per chip. However, when the atomic scale is reached, the classic paradigm of the Turing machine is no longer valid, that is, we must think of a computing model based on the laws of quantum mechanics. It is precisely at this point that arises what we call quantum computation. The qubit and its properties. Unfortunately, the computer I am using to write this text is not quantum. In it, the processing of information still follows the classical physics paradigm. And yet, in it, a bit of it can be simulated by a charged or not a capacitor, the magnetization of a hard drive, or any other mechanism that provides us only one result at a time, on or off, 0 or 1. We can make a very simplistic representation of a bit using a coin. To this end, we represent the result face with 0 and the result crown with 1. As we intuit, the coins are macroscopic objects governed by classical physics, so just get one of the results, 0 or 1, in each move. However, If the currencies behave like microscopic objects that obey the principle of quantum mechanics, we would have to face cheeks and crown could be seen at the same time, i.e. the toss of a coin, the head result, and crown coexists. This result is possible thanks to the properties of quantum mechanics called superposition. The superposition of states, although it seems a bit strange, can be understood through an analogy known as Schrödinger's cat. To explain the details of the solutions of the fundamental equation of quantum mechanics and the principle of superposition, Schrödinger proposed a thought experiment in which a cat used can supposedly be dead or alive at the same time. In this sense, that cat Schrödinger alludes to this curious quantum property as made explicit below. Consider a cat struck in a box where there is a container with radioactive material that has 50% chance to issue a radioactive particle every hour, and a Geiger counter. The Geiger counter is a device used to detect radiation. If the material is releasing radioactive particles, the counter senses the presence and drives a hammer, which in turn breaks a bottle of poison. Of course, when spending an hour, it will have occurred only one of two possible cases. The atom issued a radioactive particle or not issued, the probability that one or other event occurs the same. As a result of the interaction inside the box, the cat is alive or dead. But we cannot know unless you open the box to prove the hypothesis. If we try to describe what happened inside the box using the laws of quantum mechanics, we will come to a very strange conclusion. The cat would come outlined by an incredibly complex wave function result of the superposition of two states, combining 50% live cat and 50% dead cat. That is, by applying the quantum formalism, the cat would turn live and dead, corresponding to two same states. The only way to find out what really happened to the cat will perform a measurement. Open the box and look inside. In some cases, we locate the cat alive and the other a dead cat. It is why when performing the measurement, the observer interacts with the system and the changes, breaking the superposition of the two states, causing the system to be observed in one of two possible states. And that's a simplistic way to explain what we call the wave function collapse, which is a characteristic of the measurement process in quantum mechanics. And then, when a qubit is measured, the result will always be 0 or 1, probabilistically. Note that the qubits are mathematical objects with certain specific properties that can be implemented as real physical objects. Examples of physical systems that can be used in quantum computers to represent qubits are the different polarizations of a photon, aligning a nuclear spin in a uniform magnetic field, the two states of an electron orbiting an atom. Quantum algorithms. Anyone who has some knowledge about computers knows that to develop a computer-given task is necessary to program it. And before that, it is essential to make a good algorithm. Put just, and we can say that an algorithm is a set of procedures to accomplish a certain task. For example, we develop an algorithm to change the flat tire of a car, where we realize that two steps are replaced. The success of the task will be committed if the algorithm does not make clear that the screws should be loosened before getting up the car with the monkey. Accordingly, a program will be better as the algorithm that is based is more efficient. Fortunately, our computer scientists, system analysts and other related professionals are very competent in developing algorithms for computers that we have today, so that numerous programs facilitate our lives and allow lay computing, like me, use this awesome machine. However, with the advent of quantum computing, these programs will be obsolete. Or rather, not only these programs, but the theory used to elaborate them will become obsolete. Thus, when this new revolution occurs, the programs should be constructed from quantum algorithms. It is precisely at this point that appears a new challenge, because with this new paradigm, future developers should know well how information should be treated in quantum perspective, so that whole knowledge of quantum mechanics no longer be a restricted privilege to physical. Currently, there are already some proposed quantum algorithms, which somehow have a considerable advantage over classical algorithms. One of these quantum algorithms was developed by Peter Shor in 1993. When the proposed algorithm, Shor worked at AT&T Company and developing research that pointed advantages of quantum computers about the Turing machine. In this scenario, Shor formulated a quantum algorithm that allowed decomposing a number with many digits in its prime factors. The key detail is that Shor's algorithm performs this task in many times smaller than the amount spent by classical algorithms. The problem of factorization is essential for the current cryptographic systems, so that the proposition that any algorithms jeopardize security system, banks and governments from the time when the first quantum computer starts. Another quantum algorithm worth mentioning was proposed by the Indian Lev Grover in 1996 while working at Bell Research Laboratories in the United States. Grover proposed a search algorithm which, as its name suggests, performs the task of searching a database, finding items that have certain desired properties. We are accustomed to using some kinds of systems like these when we use the internet. By way of illustration, consider a task in which classically would need 10,000 searches. Thus, quantum would require only Grover 100. The algorithm may be successfully applied in practical problems of molecular biology and genetic engineering. Thus, by these two examples of quantum algorithms, we realize that quantum computers may, in fact, revolutionize the way we treat the information being necessary for it to new quantum algorithms are developed. It is a great challenge for the future of computing. Neural networks and quantum computing. An interesting application of quantum computing concepts is neural networks. The neural network model was constructed based on the human brain because this renders information in an entirely different way than a conventional digital computer. The brain can be considered a highly sophisticated computer, non-linear and parallel, which using its constituent neurons, performs processing such as perception and motor control, much faster than any modern digital computer. In his book, Hyken says that the human brain at birth has a great structure and the ability to develop their rules through what we usually call experience. It will be accumulated over time, with the most dramatic development occurs during the first 2 years of life and continues far beyond that stage. Thus, a neuron development is synonymous with the plastic brain plasticity which allows the developing nervous system adapts to the environment. Mobility is essential for the functioning of neurons as information processing units of the human brain, and also it is the formation of neural networks built with artificial neurons. According to Hyken, a neural network, in its most general form, is a machine that is designed to model how the brain performs a particular task or function of interest. The system is typically built using electronics or programming is simulated by a digital computer. To this, author can define a neural network as an adaptive machine as follows. A neural network is a processor massively parallel distributed, consisting of simple processing units that have the natural propensity for storing experiential knowledge and making it available for use. It resembles the brain in two respects. Knowledge is acquired by the network from its environment through a learning process. Connection strengths between neurons, known as synaptic weights, are used to store the acquired knowledge. The procedure returned to the network learning training process is called learning algorithm, whose function is to modify the synaptic weights of the network in an orderly way to achieve a goal of the desired project. It is also possible for a neural network to amend its topology, which is motivated by the fact that the human brain neurons can die and new synaptic connections can grow. Neural networks are also found in the literature with the names of neurocomputers, connectionist networks, processors, parallel distributed, etc. Physical realization of quantum computer. The experimental quantum computing is currently facing a scenario very similar to the traditional computer found in the 30s because it was not known what would be the best technology for computers. Similarly, several practical alternatives are being tested to stimulate the qubits of quantum computing, among which include quantum dots, nuclear magnetic resonance in liquids, ion trap, superconductors, among other systems. Thus, several prototypes of quantum computers that use little more than a qubit decade have been successfully tested in laboratories around the world. These tests have demonstrated the functioning of quantum algorithms so far discovered. The great challenge is to increase the number qubits in a controlled manner, and certainly relevant research on this topic will be supported in nanotechnology. In this way, even not knowing what would be the best technology for the development of quantum computers, we already know the 4 basic requirements for the experimental implementation of quantum computing. These requirements are as follows. First, the representation of qubits. Second, controllable unit developments. Third, preparation of qubits' initial states. And fourth, as the final state of qubits. Computing has gone through an intense development in recent years. The number of transistors on a processor, according to Gordon Earl Moore, scientist, would double every 24 months or so. These transistors are fundamental devices for the processor to perform the calculations. The forecast given by Moore became known as Moore's law and referred to the ability of computers that theoretically would double every 2 years. Companies like Intel and AMD continually release faster processors ever, and for that, ever smaller portions of materials are handled. Some transistors began to be manufactured with only a few molecules, so that's hard to overcome its size, expanding the capacity of electronic devices. The laws of physics about objects smaller than atoms are different from what we have learned, and we are accustomed. In this subatomic world, energy is lost or gained in a quantized way in energy packets called quantum. Several packages are called quanta. For example, a light quantum is known as a photon, which is also the smallest possible portion of light energy. Subatomic particles can also take on several different states simultaneously, so that the viewer determine your current state. Used computers to classical physics study work with 2 states which are represented by 0 or 1, and each of these numbers is called a bit. In a quantum computer, the particles could take the value 0.1 and even both simultaneously. These values are called qubits. The use of a simple form of qubits can exponentially increase the processing capability of a device. You can have a basic literature review on quantum computing, where we saw that this promising area of science proposes to merge the ideas of quantum mechanics and computer science. We note that despite the paucity projects to construct quantum computers showed many developments are possible and applicable even in the classical computer. We also realize that the adoption of the quantum paradigm in computing, it is a natural path because it walks concomitant with the reduction of electronic devices in the computer as already provided Moore's law. Note that quantum computing is not, as some may mistakenly think, one more among many attempts replacement of a depletable technology. It is a new paradigm of computing that can have profound consequences not only for technology but also to information theory to computer science, and science in general. We imagine that just as computing began in the last century brought numerous applications that have contributed to the development of humanity in various areas, and quantum computing will also provide applications that reach from space travel to medicine, increasing thus the quality of life of people. We hope, therefore, that the pedagogical way in which this was drawn up and its language easy access allows more and more people know about this new field of science and, who knows, some do not develop an aptitude for research on this vast and fruitful subject.